All right, here we go. Unit 1, Day 6, Take 17, the Intermediate Value Theorem. Today, we're going to talk about the Intermediate Value Theorem with a focus on being able to check the conditions that need to apply to a function in order to be able to apply the Intermediate Value Theorem, and how to use it to prove the existence, notice the word existence here, of some function values. This is the first of what we're going to call in AP Calculus the existence theorems. They're going to tell us that our function must be equal to some value at some point, even if we don't know what it is. So what the intermediate value theorem says is, if a continuous function, so a smooth function that you can draw the entire thing without lifting up your pencil, no breaks, no jumps, no vertical asymptotes, has an interval of a to b as its domain. So here would be our domain from a to b, and values of f of a, I'll underline these so you can see them. F of a, right, that's your output, that's your y value. F of a is right there, if this is a and this is b. And f of b, draw straight over, there's f of b. At the end of each end of those intervals, so from a to b, then f of x must contain every single value between f of a and f of b at least one time. Meaning everything on that interval between a and b, there is no way that I can draw a continuous function between these 2 points without hitting that y value, which we're going to call f of c, at least one time. Now maybe I hit it multiple times, right? Maybe if I want to get from point A to point B, maybe my function cycles up and down and it goes through that f of c multiple times. That's why this is called an existence theorem. All it does is it proves that our function hits that y value f of c at least one time. Let's take a look at what this looks like in practice. And I'm going to give you the function here as kind of training wheels, but you're going to see that you actually don't need the function to use the intermediate value theorem. So if we had the function x cubed plus 2x minus 1, and I want to prove it has a 0. So I want to prove there's some x value c for which f of c equals 0, so for which we cross the y-axis, on the interval 0 to 1. So all I care about is this interval here from 0 to 1. I'm trying to prove, without looking at the graph, that that x-intercept exists. And the way we do that with the intermediate value theorem, first, we state that the function is continuous. F of x is continuous. In this case, it's continuous because you have a cubic polynomial function. There's no reason you'd be dividing by 0 or taking the square root of a negative number or the other sorts of things that would give us a discontinuity. Second, what we want to do is we want to establish the endpoints on our domain of 0 to 1. So I'm actually going to write out, let's see what f of 0 is. F of 0 equals, and I'm just going to plug in 0 cubed plus 2 times 0 minus 1. Do all that out, you get negative 1. And just for a sanity check here, f of 0 is in fact negative 1. Next, we're going to check f of 1. I'll do that one in green. F of 1, because that's our b value, our other endpoint, is 1 cubed plus 2 times 1 minus 1. You do all that, you're going to have 1 plus 2 is 3, minus 1 is 2. And as you can see here, we have an f of 1 value of 2. The way you apply the intermediate value theorem is you finish this off by saying, since 0, because we were trying to find the 0 of the function, is between f of 0 and f of 1, f of x equals 0 at least once on, and you say your interval, on the interval 0 to 1 by the intermediate value theorem. And that is the formal way I could cover up this entire graph and you would still have proved the statement to me. You would have said that when x is 0, my y value is -1. When x is 1, my y value is 2. If I have a continuous function, I can't draw between those 2 points without crossing the x-axis. The same logic that if I just told you, try to draw between the red and, just to make this not as confusing, try to draw between the red and green dot without passing through the x-axis. It's not possible if your function is continuous. So that's the intermediate value theorem. Let's go ahead and take a look at applying it in a couple of situations. First, I want you to take a moment to try what we just learned. Try to write a full statement of proof. And I'm going to tell you what things you need to look for in your own proof to have earned full credit. So I want you to apply the intermediate value theorem to show that f of x must equal 5 on the interval 0 to 2 at least one time for the function f of x equals x squared minus 4x plus 7. In the open-ended response box, I'd like you to go ahead and write out an entire statement, because f of 0 is this and f of 2 is that, and so on and so forth. Write out your full open response, and then I want you to check with my rubric. So to check your own, the first thing I want you to look for is I want you to make sure that you hit criteria number 1. Make sure that you actually wrote out, that you actually established continuity. And so this could be anything along the lines of f of x is a polynomial, it's a quadratic function, therefore f of x is continuous. If you've gotten that, you can go ahead and give yourself a point. Second, make sure you went ahead and worked out f of 0 to be 7, and that you worked out f of 2, 2 squared is 4, 4 times 2 is 8, 4 minus 8 is -4, plus 7. Make sure you worked that out to be +3. That would be your next 2 points. And finally, make sure that you made a statement applying the intermediate value theorem. So something along the lines of 5 is between f of 0 and f of 2. Therefore, by the intermediate value theorem, f of c equals 5 at least once on 0 to 2. So go through, take a minute, compare your own answer to that one, and make sure that you hit the key points there, that you established continuity, you told me what the endpoints are, and that you use those 2 pieces of information to say, hey, if I've got to get from 7 to 3 on a continuous function, I can't do so without passing through 5. And that has to happen on the domain 0 to 2. Therefore, by the IVT, I must have an f of c equal to 5 at least once. We're going to finish off today with just a couple of multiple choice questions. First, multiple choice number 1. It's just got 3 possibilities. Let f of x equal the cube root of the cosine of pi times x. And here is a sample justification proving that f of x must be equal to 0.1 at least once on the interval 1.5 to 2. So Isaac writes, since f of 1.5 is 0 and f of 2 is 1, 0.1 falls between f of 1.5 and f of 2. 0.1 does fall between 0 and 1. So according to the intermediate value theorem, f of x equals 0.1 must have a solution when x is between 1.5 and 2. Go ahead and tell me, is that a complete justification? Did he not establish that 0.1 is between 1.5 and 2? Or did he not establish that the function f is continuous? So it turns out The actual f of 1.5 and f of 2, those are correct. Just to quickly see here, f of 1.5, because I know we need a little bit of practice with these trig rules, the cosine of 1.5 pi. And so if you think about really quickly your unit circle, we would normally call that 3/2 pi. So pi over 2, pi, 3 pi over 2 is right here on your unit circle, so our cosine is 0. So this is just the cube root of 0, which is 0, so that's correct. F of 2 would be the cube root of the cosine of 2 pi. Cosine of 2 pi, now we're all the way around our unit circle. Our cosine, so first cosine of 1.5 pi equals 0, and here the cosine of 2 pi equals 1. So this is the cube root of 1, which is 1. So those are correct. What actually never happens is Isaac never establishes that f of x is continuous. And it is. The cosine function is continuous, and the cube root of the cosine function is also continuous. So that was the problem with this one. Last for today, this is an actual AP multiple choice question from the 1997 exam number 81. Let f be a continuous function on the closed interval -3 to 6. If f of -3 equals -1 and f of 6 equals 3, then the intermediate value theorem guarantees which of the following pieces of information? I'm going to go ahead and cross out B for you. B is something we're not quite yet ready to understand that terminology, but the rest of these you can pick between. Okay, so let's look at a visual. We are on the interval -3 to +6, 1, 2, 3, 4, 5, 6. This is our domain. And we are told that f of -3 is -1, and that f of 6 is 3. The intermediate value theorem, does it guarantee that f of 0 equals 0? So let's see. Does it guarantee that I pass through the origin? No. I could draw all kinds of functions that get from point A to point B without passing through the origin. So it's not A. Does it guarantee that f of x is between -1 and 3 for all of these values? This is the y coordinate. It's saying, does our y coordinate have to be between -1 and 3 like that? No, you could go up and all the way down and do all these kinds of things. That's totally fine. There's no reason that we would have to be between those two red dots always in our range. So it's not B. Well, it's not C. F of C equals 1 for at least one C between -3 and 6. Meaning, do we have to pass through y equals 1 at some point between -3 and 6 in x? That turns out to be true. There's no way to get from one red dot to the other without at least once crossing the line f of c, right, which is y equals 1. So that correct answer there is going to be D. Just to make sure here, the last one, E, says f of c equals 0. So we'd be talking about the x-axis for at least one c between -1 and 3. The issue here is that the domain isn't wide enough. The domain here is only between -1 and 3, so that doesn't necessarily have to be the case. I could immediately shoot up here and go over. And then I would never hit the x-axis on the domain -1 to 3. The correct answer is D.